Lesson 9.1 Quadratic Models. Quadratic functions can be used to represent many real-world situations, and we need to review graphing parabolas before we get into those types of situations. So let's graph the function f of x is equal to x squared plus 2x minus 2. Now we can do this in two ways. We can make a table of values, or we can use the vertex, axis of symmetry, and then the y-intercept. I'm going to try the vertex, axis of symmetry, and y-intercept first. So I'll start with the axis, and the axis is x is equal to negative b over 2a. So b is negative 2, and a is 1, so I get negative 2 over 2. So my axis of symmetry occurs at negative 1. So that's this line here. Now that I found my axis of symmetry, I can use that to find my vertex. My x value is going to be negative 1. I just need to find my y value. So I set my function equal to y. Plug in negative 1 for x. And I get 1 minus 2, so that's negative 1 minus 2, so negative 3 is my y. And then to find my y-intercept, again, I set my function equal to y, and I plug in 0 for x. And so my y-intercept is equal to negative 2. So now I'll plot my points. My vertex occurs at negative 1, negative 3. My y-intercept is negative 2, which is 1 away from my axis of symmetry, so I go one more. Now, this gives me a u, and that's my graph. Graphing my next function, I'm going to start with my axis of symmetry. So I get negative b over 2a. So I have negative 4 over 2 times negative 1. That's negative 4 over negative 2, which is positive 2. My vertex occurs when I plug in 2 for x. So I'll have negative 4 plus 8 minus 3, which is 1. And then my y-intercept. Now you may have noticed, or you may have not, when I plug in 0 and 0, I'm left with c. So the y-intercept is always that y equals c. So my axis of symmetry occurs at 2. And that's this line here. My vertex is at 2, 1. My y-intercept is at negative 3. I'm 2 over, so I go another 2. And as you can see, I'm now an upside down parabola. And that is because my leading coefficient was negative. Next graph. My axis of symmetry is negative 4 over 2 times 2. So that's negative 1. My y-intercept is 1. My vertex, I have y is equal to 2 times negative 1 squared plus 4 times negative 1 plus 1. So that's 2 times 1, which is 2, minus 4 plus 1, which gives me negative 1. So my axis of symmetry occurs at negative 1. My vertex is at -1, -1. My y-intercept is at +1. That's 1 over, so I go another 1 over. And here is my parabola. Now, I prefer to use the axis of symmetry method whenever possible. However, I do sometimes use it. And when I use a table, is when my axis of symmetry is not a whole number. That's when I'll use a table. Okay. Now that we've reviewed graphing, let's talk about the domain and range of quadratic functions. The first quadratic we graphed gave us this graph. Now, we didn't have it as zoomed in as this, but we want to talk about this. Okay, the domain. As the graph travels up, it'll continue to go this way, and it will continue to go this way. And as it's going up, it's also going wider and wider and wider, and it will go that way forever. So the domain of a quadratic will be all real numbers. And the domain of a quadratic is always all real numbers. So you can write it out, all real numbers. You can do the symbol for R, for all real numbers. Now the range is limited in a quadratic. And what we'll do to find the range is we look at the lowest or highest y value. Now in this case, our graph is opening up, so we have a lowest y value. This is known as a minimum. If we're turned the other direction, we have a maximum. Okay, well our minimum is the point -1, -3, and our range goes from -3 up forever. So just remember, domain are x values, and range is our y's. So our range, we put it in set notation, you put y and then a line, which stands for such that. So y such that y is greater than or equal to -3. This tells me that every y above -3 is in our set of values, but below -3 we do not have any values. So let's look at the next one that we had graphed. Okay, my domain, again, are my x's. So this is all real numbers. And my range are my y's. In this case, I'm going to have a maximum right here, my maximum. And this is the point 2, 1. Now from there, my graph is going downward. So all of the values below this will be valid. So my range will be the set y such that y is less than or equal to 1. Why don't you go ahead and try to name the domain and range for this particular function. Pause the video, and then when you're done, unpause it and come back and check. Okay, our domain again is all reals. Our lowest point here is -1, so our range is y such that y is greater than or equal to -1. Okay, let's talk about the average rate of change in a parabola. Again, we're going to look at the same graphs that we've already functioned. Sorry, the functions that we've already graphed. Okay, and what we want to talk about is when the graph is descending, when it is ascending, my min or max, my vertex, okay. So when I'm descending, I'm moving downward. We always read a graph the same way we read a page in a book. We go from left to right. So we move in this direction. So when I'm descending, I am moving down like that. So I'm descending when x is negative infinity to the point -1. Now I'm ascending as I go up like this. So I'm ascending from -1 to positive infinity. My minimum or my maximum, in this instance it's a minimum, is the point, well, y equal to -3. But it's also my vertex. So it's the point -1, -3. We can talk about the axis of symmetry from the picture. We had already graphed that. But my axis of symmetry was x is equal to -1. Okay. Now, if we were to apply this, we don't have a straight line, so we don't have a slope, so we don't have that kind of a rate of change. But we can determine if, for example, the x-axis was time. We could say at 1 second, we're almost at 1. Whatever this was, 1 ball of wax or something. Let's look at the next one. Okay, again, we have ascending, descending, our min max, which is our vertex. Okay. In this particular graph, I have a parabola that's down. So instead of descending first, I'm ascending first until I get to this point here. So this side I'm going up. So I'm ascending from -infinity to +2. And then I start descending, and I descend from 2 to infinity. My minimum and maximum, in this case it's a maximum, is the point 2, 1. Okay, so why don't you try this one? Say when you're ascending and descending and what the min max is. And then unpause the video and come back and check your work. Okay, so we're ascending from the point -1 to infinity. We're descending from -infinity to 1, and our minimum is -1, -1. Okay, let's talk about transformations. Well, first we want to talk about a parent function. Now, a parent function is the most basic form of a graph. And the parent function of a quadratic is f of x is equal to x squared. That is the most basic form. Nothing has happened to that graph. And if we wanted to graph that, I'm going to go ahead and do a table of values on this one. So I plug in 0 for x, 0 squared is 0. If I plug in 1, 1 squared is 1. If I plug in -1, I get 1. 2 gives me 4. -2 also gives me 4. And if I plot these points, my graph has this basic shape. Okay. This is the parent function. Now, anything that causes this to change, if it moves over, if it flips over, if it moves up or down, if it gets fatter or skinnier, is called a transformation. And we have some transformation rules. F of x is equal to x squared is the parent function. That's the most basic shape. If we add k before we square, so this would be f of k plus, x plus k is equal to x plus k squared. And then you'd FOIL it out. it shifts k units to the left, so backwards of the sign. If we have k minus x, so, or x minus k, that would be x minus k squared. And that shifts to the right. Now, if we're adding something without squaring it, that moves up. So this would be, h. This would be x squared plus h. And then if we subtract, that would be x squared minus h. So you can see how this is different because this would give me x squared plus 2kx plus k squared. This would give me x squared minus 2kx minus k squared, plus k squared. Whereas this is taking the x squared and just adding a number or subtracting a number. If I make it a negative, so that's negative x squared, it flips over the x-axis. That means it goes this way. If I put the negative inside, we flip around the y-axis. So you can't really see that flip, unless, of course, you're shifted over, and then you can tell. And then if I multiply the parabola or the function by some number, if a is greater than 1, then the graph of the parabola gets stretched. It gets skinnier. If a is a fraction, the graph of the parabola gets compressed. It gets fatter. So let's look at some examples of these. Okay, so we're going to add k units to the left. So let's just say, instead of doing x squared, we do plus 5 squared. Okay, so let's graph our parent function again so that we can see the change. So here's our parent function. Now we're going to shift that 5 units to the left. So our points will be in the same relative position as far as their spacing goes. We just moved it over. Now let's say we subtract k. So instead of f of x is equal to x squared, let's say we have x minus 2 squared. Let's graph our parent function again. That gives me this graph. Graphing my parent function, I'm moving 2 units to the right. So again, same shape, same spacing, just moved over. Okay, if I add after the fact, so let's say f of x is equal to x squared plus 4, I'm moving 4 units up. So again, I'll graph my parent function. And then I move 4 units up. So we have the same basic shape, we just shifted up 4 units. If I subtract, so f of x is equal to x squared minus 3, I'm moving 3 units down. Graph the parent function again. And then we'll move 3 units down. Again, our spacing stays the same. Our shape stays the same. We've just shifted down. Okay. If we flip over the x-axis, First, I'm going to go ahead and graph my parent function. Okay. That's not good. Sorry about that. So instead of x squared, I have negative x squared. I flip over the x-axis. So I get all of the points, all my y values are opposite. If the negative is inside, like that, we flip over the y-axis. Now we can't really see this because what's happening is I'm going to get the exact same points. If I flip over the y-axis, this point moves to here and this point moves to here. So it looks the same when you flip over the y-axis. The only time it might look different if you flip over the y-axis is if you have one over here like this. When you flip over the axis, you get it over here like this. So that will change things if you have more than just that negation occurring. Okay, finally we have our two possibilities. So let's do a greater than 1. So we will make this 2x squared. And then down here we'll do a fraction and we'll say 1/2 of x squared. So we can compare the differences. All right, I'm going to draw my parent functions on each of these. Remembering that the parent function is just a plain old x squared. Okay, now if I do 2x squared, my 0, 0 stays the same, but when I plug in 1 squared times 2, so I get 2. And then when I plug in 2, I get 8. So that's 7, so I'd be up here. So as you can see, I'm being stretched out, which makes me skinnier. Now if I have 1/2 of x squared, I get 0, 0, but when I square 1, I get a half. And then 2 squared is 4, but half of that is 2. And then if I did 3, 3 squared is 9, but half of that is 4.5. And so you can see that I get a fatter graph, but that's because it's been compressed. It's been squished down this way. So those are the basic transformations, and those can be combined, and you'll learn more about that later.